The next examples in 4a and 4b, we're going to be using power reducing identities to solve trig equations. So this is still under our main objective to use these power reducing to solve trig equations. So if we look at our equation that we have, we got our sine or cosine of the fourth of alpha minus sine of the fourth of alpha equals a half. It takes a little bit of thinking about this, but what you can do with this is you can actually take this equation and factor it first. You don't have to use a power reducing formula right away. So my first approach to this is to use this and factor it as a difference of two perfect squares. So this is going to be the cosine squared of alpha minus the sine squared of alpha. I'm going to take that times the cosine squared of alpha plus the sine squared of alpha. Now, it had a very strategic advantage of doing that because as soon as we did that, then this part here is a Pythagorean identity, which is nothing more than 1, so it's just the cosine squared of alpha minus the sine squared of alpha that had to equal a half. So that reduced half of our work immediately. Now what we can do is we can come back and use our power reducing formulas. So we're going to take our cosine squared of alpha and we're going to rewrite that as 1 plus cosine of 2 alpha all over 2, then minus 1 minus cosine of 2 alpha all over 2, and we're going to try to get that equal to a half to solve our equation. Well, we already have our common denominator, so really what we need to do is we need to distribute the subtraction and then rewrite our fraction. So it's going to be 1 plus the cosine of 2 alpha minus 1 plus the cosine of 2 alpha all over 2 equals a half. So simplifying, we can collect our like terms. The -1 and +1 will cancel. We'll end up with 2 of these cosine of 2 alphas all over a 2, and that equals a half. And then I'm going to reduce the 2's, and we're going to get the cosine of 2 alpha is equal to 1/2. And now we're going to solve our resulting equation. Rather than using a double angle identity, it's much easier just to go ahead. We can undo the cosine, and we can say 2 times our angle alpha has to equal the angle whose cosine value is a half. Our cosines are only positive in a couple of quadrants, the first quadrant and in the fourth quadrant. So here's our choices. If it's our first quadrant angle and the cosine value is a half, this is the x value over the r, so 2 and 1 square root of 3. So we're looking at an angle of pi thirds. It means our reference angle down here is pi thirds, which means in standard form, the angle that we're looking for is, let's see, 5 pi thirds. So double our angle has to equal one of these two results, and one is pi thirds, and the other one is 5 pi thirds. And they didn't give us any restriction on our domain that I can remember, so we got to think of this in terms of all the angles that we could possibly get. So we're going to add on plus 2 pi n to take care of all of our wraparound angles. And that's what 2 times the angle has to be. So in order to find the actual angle we're looking for, we're going to take everything times a half. So both sides times a half. So that means 2 times alpha is going to equal half of pi thirds, which would be pi 6, plus half of 2 pi, which would be pi n, is one of our solutions. Then we take half of 5 pi thirds, which would be 5 pi 6, plus then half of 2 pi n, which would be pi n again. Okay, so that is what alpha is, since I already divided by 2, and now those are all of our possible solutions to this equation. Okay. I'm going to split this one up again just as I did the other video, so I'm going to stop on this one, and then we're going to go grab 4b with a separate video.